right, so before we begin on our journey to fulfill this lesson objective about being able to find the derivative of an inverse function, which we said is something to do with being totally upside down, let's look at some properties, some calculus kind of properties of inverse functions in general. Okay, so this is basically four little theorems here. Let f be a function whose domain is an interval I, and if f is a one-to-one function, then the following statements are true. So let me pause right here. One-to-one function, let's review that. This idea of being a one-to-one function is important. Why am I on red? I don't know. So one-to-one means two things. It means every input has one output. That's what it means to be a function, right? One output. If I stick something in, only one possible thing can be spit out. That's, again, a function. Okay, but every output has one input, right? It's the, it switches that. Every output has one input. Okay, now this first one, like I said, every input has one output. That means it's a function. And that's not how you spell function. Okay, moment of dyslexia. Anyway, so this passes the vertical line test. You remember the VLT from Algebra 1. Sounds like a not quite so delicious sandwich. Anyway, every output has one input. This means that the inverse is a function. And that's pretty important because that's what our lesson's all about. Okay? Like, for example, if we think of a parabola, if I draw one of these things, this is a function for sure because every input has one output. It passes the vertical line test. However, it does not pass the horizontal line test, the HLT, right? So if I were to draw a vertical line in here, sure, it passes that. Horizontal line, it does not pass that. Therefore, it's not a one-to-one function. What that means is that, sure, it has an inverse. Every function has an inverse, but it's not necessarily true that that inverse is in itself a function, right? If I were to, let's say, grab this green color here, its inverse is like that, and then I can see that that inverse is not a function. Okay, we want only the kinds that are one-to-one functions. Here's an example that you've been seeing every day of your high school life, just about. We have that e to the x, we have that natural log of x. It is a one-to-one function, passes both the vertical line test, horizontal line test. Every input has one output, every output has one input. If you take a look at the graph that is right over here, here is a sample generic graph of something that's just called f of x. And as we spoke about, you can form graphically, geometrically, the inverse by just reflecting your graph across the line y equals x. That takes the point a comma b and maps it to b comma a, right? Okay, now some things about this. Notice that this function, the original one, is continuous. If you just swap your x and your y coordinates, assuming that this function here has a point at every, value in its domain, if I just swap the x and the y value, doesn't it make sense that this one would be continuous as well? Right? Now here's another one. Notice that this function, moving from left to right, is going upwards, increasing. It's increasing. Well, what about its inverse function? Isn't it still going upwards? That is one aspect of inverse functions that we don't usually think about or maybe even anticipate. Oh, if one's increasing, then the inverse has to be decreasing. It's not true. Increasing and increasing. Let's see. A differentiable. Notice that there are no sharp turns. There are no discontinuities in this thing. There are no vertical tangent lines. There's a horizontal one, no vertical ones. But take a look at this over here. Is the same thing necessarily true about this one? Well, if I were to approach this particular point right here, this is going to a vertical tangent line. Where did it come from? This point came from this point here. which would have been a horizontal tangent line. Very important. Okay, so let's now write down these 4 statements that have to be true about the continuity and differentiability of inverse functions that are one-to-one, or functions that are one-to-one. Okay. If f is continuous on its domain, then the inverse is also continuous on its domain. All right, again, we are just swapping the x and the y value, assuming that our x and our y value originally exist, so will just swapping those two things. Okay, next one. As we mentioned, if f is increasing on its domain, then the inverse is also increasing on its domain. Likewise, if f is decreasing on its domain, then the inverse is also decreasing. We didn't have a picture of that one specifically, but it's, it's directly related to this one that's over here. All right, and the last one has to do with differentiability. If f is differentiable on an interval containing c, and the derivative at c is not 0, then the inverse is also differentiable at c. This means that at every single point on your original function, if it's differentiable, then so will the inverse function be differentiable. With one exception, wherever the derivative is equal to 0, then it's not going to exist over here, as we saw between these 2 points.